Let's get ready slowly. So we are going to talk, today is going to be a super boring lecture, so be excited. I'm sure that you're all overexcited about the super boring lecture because we are going to talk about thermodynamic potentials, which is the thing that everybody hates because you never understand why the hell should one have thermodynamic potentials? Why are they useful and why should we use them? And what is the enthalpy, Gibbs free energy, Helmholtz free energy, this, that, ground potential, and so on and so forth. It's complicated, I know, because it's essentially try to find a function that describes a system in certain conditions in which you fix a certain subset of thermodynamic variables, okay? And in particular, a function that tells you what is the condition of thermal equilibrium if you do that. Anyway, so last time we've been introducing entropy, the state function entropy, right? And what we said is that entropy is defined as by this integral, where the integral is computed along a reversible transformation connecting 2 points A and B. And in particular, if you want to define the state function entropy, you have to decide what is your reference point, and your reference point as to is the zero temperature state for which you decide that entropy has to be equal to zero, the so-called third principle of thermodynamics that is impossible. No, third principle, not third impossible, third principle. It is, in my opinion, very hard to understand if you don't know statistical mechanics, and in particular, quantum statistical mechanics. Okay, so it is quite crucial to have it in mind. Okay, so this said, in practice, the most important thing that we will use concerning entropy is that the heat exchanged with the environment is equal on an infinitesimal reversible transformation is of course equal to TdS, right? And so that's the most important statement. And of course, yeah, so that's what it is. All right, so now this said, let us derive some consequences of this definition. First of all, question number one, what kind of thermodynamic variable is the entropy? Is it extensive or intensive? Intensive?
I think about it.
You know, let's use, is it intensive to extensive? Third, both. Both, it's impossible. So what is it? The second is extensive. Why? Why is it extensive?
Depends on the.
What?
Depends on the. It depends on external elements.
No.
Depends on the size of.
Yeah, no, of course, that is the definition of extensive, right? So, but why is it extensive? Look at the definition. Why is it extensive?
The temperature.
No, the temperature is intensive. The temperature is intensive, right? If I take this room and I say it's at, you know, I don't know, outside is probably here is 20 degrees. And then I open the door and then I have the rest of the room, it's still 20 degrees. It doesn't depend on the volume. It's intensive temperature. So
Because of the heat.
because of the heat exchange with the environment is essentially a form of energy transfer. And of course, it's extensive, right? You know, let me make the following example. Suppose that you have this room. We close the door, we have the air inside this room, which is about at 20 degrees. And then we decide to bring it to 0 degrees by, I don't know, opening the windows in the room. Well, that's not good, but by transferring the heat inside here outside. Of course, the amount of heat that you have to transfer out to bring it to 0 degrees depends on how big is the room, right? And that you would see, because if you need to cool down this room, you need a big refrigerator. If you want to cool down a small, something small, you need a small refrigerator, right? You pay less. So it's extensive amount of heat. And that we understand very well. Okay, so this said the heat, the entropy is an extensive quantity. So this is the correct answer, because it's because of the definition. Okay, so now let's see what is the consequence of the fact that the heat is an extensive quantity, which are the so-called Gibbs. No, not yet, not yet. We will get to the Gibbs potential later. Look at relations. What? Duhem. D-U-H-E-N.
What's the first word?
Relations. Relations. You know, I can do this. Take it. And then resize. So relations. Okay. Now you see it better. Anyway, so what does the Gibbs do in relations? Well, we know because of the first principle that du is equal to dq minus dw, right? Now, therefore, since dq we know what it is for reversible, infinitesimal reversible transformation, is TdS minus dw, right? And this is equal to TdS plus sum over I yi dxi minus plus sum over alpha mu alpha dn alpha. So these are the generalized forces and generalized let me make an example. If you have pressure and volume, then Y is equal to minus the pressure, and then Xi is equal to the volume. The reason I'm writing it this way is that I could, in principle, have some magnetic work, some electrical work, if I have dipole moments, and so on and so forth. So I'm writing things in the most general way. And this is the chemical work, right? So chemical potentials times changes in the number of particles. All right. So from this formula, you get that the temperature is du ds with the others constant. Then the generalized the analogs of pressure is du dxi with the other constant, so temperature and alpha, and all the other xi with I not equal to, well, with j not equal to I. And then I have the chemical potentials equal to du dn alpha with the other variables fixed. Okay? I mean, I didn't write anything yet, but you don't know. Now, I notice the following thing, that my internal energy is a function of, from this way of writing things, the internal energy is a function of the entropy of the various xi, volume, magnetization, total dipole moment, etc., and the various n alpha. Okay? So now all these variables here are extensive, right? I mean, total magnetization, total dipole moment, total this and that, they're all extensive variables, including the entropy, which means that if I rescale the volume,
Is that you or me?
what?
Is that you?
U, it's a U,
The iron.
is internal energy, yeah. Internal energy is a function of all these extensive variables, which means that if I rescale the volume by a factor of lambda, right? So go to v tilde, v prime, and lambda v. Well, how is this going to transform? I will get that U, the internal energy, is extensive, so it's going to rescale by the same factor. Now this is equal to U at lambda S, lambda xi, and lambda and alpha, right?
It's a linear function.
It's a, how is it called? I think it's called the homogeneous function in a sense. If you rescale all quantities by the same, get a factor of. This is actually a trivial form of scaling. In statistical mechanics, you can have more sophisticated ones. For example, close to phase transitions. This is just a trivial one. Anyway, now this relation is very important, and it's just a consequence of the fact that the system, that these variables are extensive, are all extensive variables. Okay? It's very important because of the following reasons. Suppose that I take this formula and I take a derivative with respect to lambda. So if I take a derivative of the left-hand side, I get u, right? So u is equal to what? Is equal to S times du ds plus sum over I xi du dxi plus sum over alpha and alpha du dn alpha, right? Just taking derivatives with respect to alpha on both sides. Lambda, sorry. Lambda. All right, so now let's go back. Du ds is t, du dx is y, du dn is a mu, right? You see this? 1, 2, and 3. Therefore, if I use here these three results, 1, 2, and 3, what do I get? I get this, that this is equal to S times T plus sum over I xi yi plus sum over alpha and alpha y alpha. Sorry, mu alpha, not y. Mu alpha. Right? This is just a consequence of the fact that these are extensive variables.
You mean by taking this extensive, you can rescale the homogeneous.
Yeah, so I mean, the fact that it's extensive means if I multiply the volume by factor lambda, which I multiply n alpha by the same factor, I multiply all the xi by the same factor, and multiply the entropy by the same factor. And that implies also that U is multiplied by the same factor because U itself is extensive, right? So it has to satisfy this relation. The consequence of taking the derivative with respect to lambda is this. Okay? Now, this has a deeper consequence if you think for a second. And the consequence is the following. You see that up here, I had that du, let me rewrite it here. Before, I knew that du is equal to SET plus sum over I yi dxi plus sum over alpha mu alpha dn alpha, right? This was my first principle of thermodynamics. Now, let's take this and take a differential of this formula. Yes?
The S and T are interchangeable. The S and T are interchangeable.
Absolutely. You're right. SDT. Oh. Okay. So now I take this formula and I take it a differential. du is equal to dst. Oh,
Okay. Okay.
T, yes. Okay, sorry. You know, it's the entropy that didn't want to be differentiated. It's not my fault. She was resisting differentiating. So anyway, plus sum over I d xi yi plus sum over alpha d and alpha y alpha. Okay? Now, I do this, I take this differential, I get TdS plus sum over I yi dxi plus sum over alpha mu alpha dn alpha plus SDT plus sum over I xi gyi plus sum over alpha and alpha d mu alpha, right? But now, from this, I know that these two are equal, which implies that this object here has to be equal to 0, right? This equation implies that this is equal to 0. All right, so now the fact that this is equal to 0 is quite important. Why? because it allows you to obtain formally derivatives of extensive variables with respect to others extensive variables in a simple manner. Suppose, for example, that I want to obtain the derivative of the pressure with respect to the chemical potential. So your problem requires you to find this derivative.
Both P and E are extensive.
So both variables are intensive. Pressure and chemical potential are both intensive. Right?
But you said this now you can obtain the extensive.
Then it was a mistake. I said something wrong. You can obtain derivatives of intensive variables with respect to other intensive variables. Why? Because if now I fix the temperature, right, in my system, you see that this formula here, so dT is equal to 0. Then this formula implies that minus P dV plus mu dN, sorry, confusing messing up, minus V dP plus N d mu is equal to 0. Right? If I fix temperature and I use the previous expression, that implies that this is equal to 0. And therefore, this means that dP d mu is equal to minus is equal to plus N over V. So in other words, it's the density. Right? This makes a lot of sense because, you know, this is the ratio of two intensive quantities. It has to be an intensive quantity, and the density is intensive, of course, because it's the ratio of two extensive objects. No, this is not a P, it's a rho. Rho. Okay? All right, so in other words, you can use these relations and we will use them later on in some examples. Every time you need this kind of derivatives, derivative of pressure with respect to blah, 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 derivative of temperature with respect to something else, derivative of pressures with respect to temperature, and so on and so forth. They're useful for this kind of things. And you understand what I mean. Essentially, this constraint of the fact that these functions are extensive, this relation is constraining essentially the differentials, the ratio of differentials of intensive variables in your system. All right, so that's it for the Gibbs-2M relations. And now we go to the thermodynamic potentials. And hopefully by the end of the lecture, you will understand why they're used.
So the idea behind the Gibbs-2M relations is that we take derivatives of intensive quantities to get another intensity.
Well, so you're able, first of all, to express derivatives, to calculate derivatives of intensive quantities in a simple manner. And of course, the result has to be intensive. So, you know, if you, let me make an example. If you write in the final exam, dP dt equal to, I don't know, let me think for a second, as minus S over the density, then you will get minus 10 points. Why?
Yeah, because
One is extensive, the other is intensive. So you certainly know that here there shouldn't be a density, but perhaps a volume, right? So you see, that's how it works. It's actually very quick to realize how these things work. All right, so thermodynamic potentials. Why are they useful and how to use them? Well, so thermodynamic potential, in order to introduce thermodynamic potentials, you have to have in mind always a physical situation, okay? Each thermodynamic potential is constructed to describe a certain physical situation. So, for example, let's start with a physical situation that is the following. The system is isolated, and I fix in a fixed volume. No, it doesn't need to be a fixed volume, it needs to be isolated. So then you, of course, describe the system in terms of the energy. And you know from what we just said that the internal energy is minus PdV plus mu dN. And at the same time, you know that the temperature is equal to dE du ds at constant. So whenever I put a line like this, I mean, I keep fixed all the others, okay? I don't want to write all the others all the time because it's too long, okay? That's one of the painful things about these potentials. So this is mu dV with a minus sign, and then we have the third one, which is mu equal to du dn, where I fix all the other variables. All right, so now, why all of this is useful? Because from the second principle of thermodynamics, okay, I know that if I have a transformation that is not reversible, okay, then du, well, the first principle of thermodynamics is always valid, right? So du is always equal to dq minus dw, right? But the point is that dq now is smaller or equal than TdS in transformation that is not reversible, right? Therefore, this is smaller or equal than TdS minus dw, or smaller or equal than, let's call this not du. I don't want you to get confused. Change in internal energy, or whatever. Is equal, smaller or equal than TdS minus PdV plus mu dN. Right?
Why?
Why?
Yeah, why you change the symbol of U?
Because, so this is du computed. Okay, let me not change it. This is simply on a generic transformation, irreversible. And this is the differential and infinitesimal reversible transformation. Okay? So that way we understand each other. So, which means the following, that if I do a transformation in which I keep fixed the entropy the volume and the number of particles, fix entropy, volume, and number of particles in my system, then what I know is that du in general is smaller or equal to 0, is diminishing, right? In an isolated system. At the same time, I know that if I fix, sorry, you didn't get this formula? Well, you see, if I fix S, V, and N, that means that ds is equal to 0, dt is equal to 0, and dn is equal to 0, right? So that means that du reversible is equal to 0. And therefore, du is smaller or equal to 0. So I just rewrote what I wrote above, okay? At the same time, this means the following, that if I use the first, this relation here, you see that this means in general that, just a second, I can write in general that dw is always smaller or equal than T ds minus d. And therefore, if I fix the entropy, then this means that the work done cannot exceed minus the change in internal energy.
What is capital E?
Sorry, the problem is that I have different notations in my notes and in what I'm writing. Yes.
I'm thinking of negative internal energy. So that if we have a negative internal energy, it means that
No, we don't have a negative internal energy. We have a change in internal energy.
a negative change in internal energy.
So it means that we are decreasing energy. The
Yes.
system is decreasing its energy.
But in some other ways, we think about it as the system expanding.
You're asking me what process could lead to decrease in internal energy that is isentropic. To be honest with you, I don't have in mind an example. I have to think about an example. So let's do the following. I'll keep your question in mind. You want an example of a process that is isentropic, constant volume and constant number of particles, and in which you have a decrease in internal energy. I'll give you an answer next time. Okay? So let's work this way. If I have it on top of my mind, I'll tell you immediately. But if I don't want to make a mess of these lectures are recorded as well. You know, they go on YouTube. I don't want to make a mess in public. So I'd rather give you an answer next time when I'm sure of what I'm talking about. Okay?
Is that EU irreversible?
Yes, it is not irreversible.
So from delta becomes du.
You see, that comes from this, right? No, just a second. Let me think for a second. Yes, it is the du irreversible. All right. So let's move on with the next potential. So this was describing a situation in which the system is isolated. Situation in which the system is isolated is what in statistical mechanics we will describe as kind of microcanonical. Okay, system is completely isolated, it cannot exchange any heat with the external environment, and that's it. Now, do you know any apart from the thermos and where you put your tea and the entire universe, do you know any example of a system that is in these conditions, approximately?
What the condition?
These microcanonical conditions, well isolated from the external environment,
So
cannot exchange energy with the external environment, and constant number of particles in volume. Well, volume for the universe is not true. So apart from the universe, approximately now the universe, and your thermos where you put tea, which for if you paid for a good thermos for a few minutes is approximately an isolated system. Do you know any physically relevant example of a system that is in these conditions? Is this room in those conditions? No, because the door is open. And you can exchange heat with the external environment. Okay, so this room is not in those conditions. So let me tell you, there is one system in modern physics that is approximately in these conditions, which are clouds of cold atoms in which we observe, for example, the Bose-Einstein condensation and all kinds of funny phenomena for cold atoms in optical lattices. Those systems, for the time scale of the experiment, are very well isolated from the external environment, and they are approximately in these microcanonical conditions. In practice, they are not coupled to anything else. They're just isolated. Okay? So all this to say that this is not completely irrelevant. You can have situations in which you can do this kind of physics. But the most common situation is the one we would have if we close that door, we keep the windows closed, but still our room can exchange heat with the external environment to keep constant what? The temperature, right? That's the most common situation in life, where your temperature is kept constant, that's inside. So in that case, you assume that your system is in contact with the reservoir. Is that what?
Before contact.
In contact with the reservoir. You know, you're lucky that I'm not Leonardo da Vinci, because Leonardo da Vinci would have written the other way around. So from the right to the left in Latin characters. So and then it would have been hard to decipher. In contact with the reservoir at temperature T. Okay, let me try to see if I can do this. No. No, I cannot change the orientation. Okay. All right, so in contact with the reservoir at temperature T, we introduce, you don't use the energy anymore to describe your system, you rather introduce something that allows you to fix, instead of the entropy, the temperature, right? So you perform what is, you perform a transformation that is equivalent to inserting a Lagrange multiplier in a sense. So in practice, you introduce f, which is equal, a function f, which is equal to e times t times s. What? It's a yes. Let's agree on the Silva advanced notations. U is equal to. Okay. Yes.
When the system is put in contact with the reservoir,
Yes.
it means that the particles in the system interact with the particles in the reservoir.
Yes, absolutely. They can interact. They do interact, actually. That's how heat is exchanged. You don't need to transfer particles. And that's the most efficient way, but you cannot exchange heat through the walls, unfortunately. I mean, I would love not to be able to exchange heat through the walls. This way I wouldn't pay for the heating in the winter. But it happens. Anyway, this object here is called the Helmholtz free energy. Free energy. It's a very important object in statistical mechanics. We will see when we will define the partition function for classical statistical mechanics. But for the moment, the only trick when you consider this is the following, that when I take a differential df, this is equal to du minus dTs. But TTS is TDS plus SDT, right? So this is du minus TDS minus SDT. And you see that overall, since U is TDS minus PdV plus mu dn, you see that overall the effect is that this TDS here cancels the other one and leaves me with a minus S dt. So I'm able to describe a situation in which I fix the I fix the temperature and not the entropy. Okay? This is gone, and I have the other. All right, so overall, what I have is that my entropy now is equal to what? Is equal to minus df dt with my three dots. My pressure is equal to minus df dv with all other variables kept fixed, and mu is equal to the usual df dn with all other variables kept fixed. And now I simply use what I had before for du, for the change in internal energy. In general, df for generic transformation, df, which is equal to du, du minus dTs is going to be smaller or equal than the du on a reversible transformation, which is SDT, blah, 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 TDS, blah, blah, blah. So overall, I will get df smaller or equal than S minus SDT minus PdV plus mu dn. What? No, SDT. It's correct. Minus SDT. Right? Because the TDS is gone. And what remains is SDT. So that's correct. Now, this beautiful formula here, well, beautiful. So what I'm saying is the following. On a generic transformation, I would define my Helmholtz free energy in this way. And then I know that the U for a generic transformation is more or equal than what I found before. I substitute then the one for a reversible transformation. I substitute it, and this is what I do. Okay? Which means the following, that if I fix temperature, I fix the volume and the number of particles, then EF is always more or equal to 0, right? Which, by the way, tells you that what is a stable state, what is the equilibrium state under these conditions. Suppose that I give you a system in which I fix the temperature, I fix the number of particles, and I fix the volume. What is the equilibrium state for this system? What is the equilibrium state for this system? The equilibrium state is a state that is, a state there forever, right?
Yeah.
Nothing changes.
It's weird. Because
Okay, let me explain. The idea is the following. If I kept these three variables fixed, since every time I do something to this system, I diminish the free energy, the only state that is always stable is the state of minimum free energy, because it cannot diminish, right? You cannot do anything to the state of minimum free energy. Whatever you do is a minimum that cannot go anywhere, right? Unless you change the conditions. And therefore, this inequality tells you that if you have a system at fixed temperature, volume, and number of particles, the state of minimum free energy is the equilibrium system, the equilibrium state, right? At the same time, I can reinterpret what I told you before. If instead of fixing temperature, volume, and number of particles, I fix entropy, volume, and number of particles, is the state of minimum energy, not free energy. That is the one, the equilibrium state. But that's obvious, right? If I have an isolated system, what is the state that never changes? It's the state in which you minimize the energy. If you minimize the energy, of course, you cannot further diminish it. Right? So that state will not go anywhere. Now, this is very important. Yeah, it looks trivial, but it's not trivial because it's actually crucially important, this fact, that the states of minimum free energy are the ones that realize equilibrium states given the macroscopic conditions. Why it is crucially important? Because when we will study statistical mechanics, we will see that there is a connection between partition function and free energy. You know already more or less what is a partition function. We will see that Z, the partition function, is e to the minus f beta f. Or f, no, and now the point is that in that context, we will see that the states of, when we, for example, perform approximations like mean field approximations and so on and so forth, the minima of the free energy will be the equilibrium configurations. So you see all of these ideas that we will see in the context of statistical mechanics to these relations actually have an origin in thermodynamics. Okay, so keep this in mind. Now, in addition to this, there is another important inequality, which is analogous to the one before. If I have a system in which I fix temperature, etc., the work is smaller or equal than minus df. Okay, All right. So now comes the thermodynamic potential, in which you, instead of fixing temperature, you fix the pressure, fixed pressure. Now, this is, for some reason, is a thermodynamic potential that I remember I've seen 3,000 times when I gave the exam of chemistry when I was a student, a bit younger than you. And I used to hate it. It's called enthalpy. H equal to U plus. Now, if I want to fix pressure, what would you add? So before, to fix temperature, I have to subtract Ts. Now I want to fix pressure. What do I have to add? PV. I have to add PV. Okay? Why? Because if I add PV and I go through all the steps and I use the U, blah, 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 I will get that this differential is TdS plus VdP plus mu dn, right? At the same time, I will get that.
Why you differentiate with PV?
Sorry?
Why is there PVP? Why are you right?
Why VdP? Well, it's simple because this is du plus dPV. So this is du plus PdV plus VdP. Now you substitute the expression for the u, which is TdS minus PdV plus mu dn. Now the PDV goes with this one, the minus PDV goes with this one, and what you're left with is only this. You agree?
Well, after that, you substitute the U expression.
Yeah, well, I substitute here the expression, let's write it here. This is equal to TdS minus PDV plus mu dn. Looks like, sounds like poetry. PDV, mu dn, poetry in French.
But why would you write fixed pressure?
Why?
Yeah.
Because I want to find a thermodynamic potential for which I can, with which I can describe a situation in which I fix pressure, volume, and number of, sorry, pressure, entropy, and number of particles. Okay. And if I do so, you see that I get ds dp dn. And therefore, at the end of the day, I will get T equal to dH ds, fixing all the other guys, V equal to dH dP, fixing all the other guys, and then mu equal to dH dn, fixing all the other guys. Okay? And then as we,
What you call
this is what they call H.
I mean the name.
Enthalpy, enthalpy, enthalpy. Enthalpy. All right, and then, well, as before, you will be able to prove that dH in general is not really equal than TdS plus PdV plus mu dn. Therefore, is always smaller or equal to 0 if I fix these three variables. Therefore, the limit of the enthalpy are the ones that realize equilibrium state of pressure. And dW, the work, is always smaller or equal than minus dH. Here's the story. And finally, so you understand how it works. I mean, suppose that instead of fixing entropy, volume, and number of particles, I want to fix temperature, pressure, and number of particles. Then, if I want to fix temperature, pressure, and number of particles, so what do I need to do? I need to take the internal energy. If I want to trade entropy for temperature, I have to subtract Ts. If I want to trade pressure for volume, I have to sum PV. And I obtain another potential, which is called the Gibbs free energy. Right? And then I will have that dG, well, you can work it out yourself. dG is equal to what? Minus STT plus VDP plus mu dn. And then, of course, dG dt is equal to minus S. dG dP is equal to V. And dG dN is equal to mu. And then if I fix these three variables, dG is more or equal to 0, and then the work is more or equal than minus dG. Usual stories. I mean, it's always the same story. The only difference is what kind of variables are you fixing? Now, what confused me the most when I was studying this stuff, when I was younger than you, is that I had to remember Gibbs, Helmholtz, enthalpy, and I would always get confused because, as I told you, I don't remember names. Simply don't remember them. There must be something wrong in my brain. Anyway, but what you have to remember is just, I start with the energy, in which I have three variables: entropy, volume, number of particles. And now I want to trade some of these variables with something else. Well, what I do is I add or subtract a corresponding term in order to make the differential appear in the correct form. That's it. That's the only thing you have to remember. Then if you want to call the enthalpy, I don't know, whatever, it's your choice. And that's just a name. But the logic, the reasoning is very simple. Okay? And so, therefore, finally,
Sorry.
yes.
I still don't get the principle. So basically, you just take U and then subtract with the term.
Let's just do the following exercise. The whole principle, you will understand it now. Super simple. So we said that with energy, we fix entropy, volume, and number of particles. Now I want to describe a situation, which is the situation of this room. This room has a fixed volume, has a fixed temperature, but is exchanging particles, right? Therefore has a fixed chemical potential, right? So what should I do in order to describe this situation? I take the energy and then well, let's first trade entropy for temperature. So what do I do to trade entropy for temperature? Subtract Ts. Good. Now let's trade number of particles for chemical potential. What do I do? Mu n. Perfect. And then we could call this the Silva potential, but unfortunately the name was already taken and it's called the ground canonical potential. So what can we do? Okay, so let's call it omega. You see, the logic is very simple, right? There's nothing to remember. It's called the ground potential. If I take the differential of this ground potential is equal to minus SDT minus PdV minus n d mu. Then, of course, I will have that the entropy is equal to d omega dt. The pressure is equal to minus d omega dV, and the number of particles is minus d omega d mu. Yes? Why suddenly?
PDP is from you. The PDP is it from you?
Yes, yeah, it is from you. Yeah. So what you do is, okay, let me do it slowly. I mean, I see that we need to do things slowly. So we agree on this. Now let's see why this works. Because d omega, yes.
In this case, the variable that are fixed are the volume, the temperature, and the chemical potential of the other.
The volume, the temperature, and the chemical potential. Fixed, yes. Well, so these are the variables with which I want to describe my system, right? The three variables. So d omega is equal to du minus dTs, which is TdS minus SDT, minus mu dn minus n d mu. Okay? And then this is equal to what? Well, du is equal to TdS. Aha, but there is a minus TdS here, so let's put it here. Again. Minus PdV, and that remains, it doesn't have any more. Plus mu dn. But there is another one here, so minus mu dn, and this one is gone. And then you will have minus SDT minus n d mu. And therefore I get what I wrote down before, minus SDT minus PdV minus n d mu. Okay? So you see, I traded S, V, and T for V, T, and mu. Now,
Do you usually have a shortcut to remember it or just?
no. Look, that's what I'm saying. I mean, my experience is that if you try to remember all the names, all the things, you have to remember the mechanism. That is common. Okay, not the names, the variables. You have to remember two things. One thing is the energy, right? The first thing we wrote down. So this expression dE equal to TdS minus PdV plus mu dn. But that is the first principle of thermodynamics. So remember the first principle of thermodynamics, and then remember the mechanism. And the mechanism is, every time I want to change variables, I have to subtract the TdS, T times S, to add the mu dn, and then I rederive everything. Then, of course, I mean, if you're good, you can remember that one is called the Gibbs potential, the other is called delta P, the other is called whatever. But if you're like me, that I could never remember this stuff. I mean, I would have to learn it like poetry. Remember the mechanism, and that's going to be fun. And the mechanism is very simple. Yes.
In the expression of omega 1, we do not write PV because they also exist.
Why I didn't write a plus PDV, plus PV? Well, because if I would have written PV here, so if I would add here plus PV, then I'm trading volume with pressure. So which means that if I add here PV, I am considering a situation in which my free variables are P, T, and mu. But I don't want this. I want V, T, and mu.
And V is inside V.
And V is sitting here, actually. Oh. Okay. Yes, just a second. Okay. Yes.
In the case of omega, the fixed variables are the temperature, the volume, and the chemical potential.
Yes.
So in this case, those variables are fixed. So why would we do the differentiation over these variables? Because
they're not fixed. No. Wait a second. I want to have a function of those free variables, right? So these are the free variables in my systems, and all the other variables have to be re-expressed in terms of them. Okay? So think about it. I know that I used the wrong words, but this is what I meant. Okay? All right, so now look at one thing. This object here, which is called the ground potential, is actually very important in physics. So we will use it a lot when we will do statistical mechanics. Why is it useful? Because of the following thing. The ground potential, as we have seen, is U minus Ts minus mu1, right? But we know from the Gibbs-Duhem relations, Gibbs-Duhem, that U is equal to Ts minus PV plus mu n. This is the Gibbs-Duhem relation. And therefore, if you substitute it here, you get that this is equal to minus PV. And now this tells you something very interesting. You remember that how does the equation of state for the ideal gas look like? P times V equal to N times R times T, right? So this tells you, first of all, if I want to get the equation of state with the ideal gas, for the ideal gas, what would I do? I calculate that. It's enough to show that for the ideal gas, the ground potential is N times R times T, minus N times R times T. In addition, if I want to generalize this equation of state for an interacting system, it's enough to calculate this ground potential for an interacting system and show how it looks like. So this is what we will develop when we will introduce the ground canonical ensemble in statistical mechanics. The ground canonical ensemble will give us a way to compute the ground potential and therefore the equation of state. Okay, so that's why it is useful. The canonical ensemble will give us a way to compute the Helmholtz free energy. That is the one describing the situation in which the temperature is fixed, the volume is fixed, and the number of particles is fixed. The ground canonical potential will give us a way to compute this in which the number of particles is not fixed, can change. The volume is fixed, and the temperature is fixed. Okay? All right, so there is one last So is it clear, this mechanism for constructing these potentials? It's very simple. It has to be clear to all of you because it's, you know, it's just a change of variables. Okay, so go through it slowly. I mean, I'm sure that if you sit down, start with the first and understand how to slowly go through it, everything is going to be very easy. Okay. It's a well, one of the two, Lagrange, Legendre, one of the two. Yes. I mean, you know, as I told you, don't remember names. I remember formulas. Probably I'm a physicist and not a poet because of this. All right. Okay, so one final thing that is crucially important is to remember Maxwell relations. So what are Maxwell relations? Maxwell relations are the consequence of the fact that these are exact differentials. So in particular, when I write, I will write, I'm not going to write down all the Maxwell relations, okay? Don't expect it from me. You go to a book, Wang, they're written down, all of them there, and it's also explained how to remember them, but I'm going to explain how to construct them, which is different, not to remember. You're not supposed to remember them, all of them. So let's start with internal energy, with what we started with. TdS minus PdV plus mu dN. Now the point is the following. The temperature, for example, is equal to du ds. But what I have to have is that, for example, one of the things that I have to have is that the derivative of the temperature, of the internal energy with respect to S, and then with respect to V, should be equal to the derivative of the internal energy with respect to first V and then S, right? These cross derivatives have to be equal to each other because it's an exact differential, right? But now let's read what we wrote down here. What we wrote down in this formula is that the derivative of du ds, which is the temperature, with respect to the volume, right, is equal to the derivative du dv, which is minus the pressure, minus the derivative of the pressure with respect to the entropy. And now you ask yourself, how will I ever remember that something of this form exists? It's actually very, very simple. You have to remember in life, in thermodynamics, you have to remember three things. Ts, T times S, mu times N, P times V. Or TdS, I like it better, they say TdS, PdV, mu dN. Okay, these are the three things that you remember. In other words, pressure is conjugated to volume. They're like couples, right? Pressure is conjugated to volume, entropy to temperature, chemical potential to number of particles. And you see that here I have the derivative of the temperature. Let's do it in another color. This one. The derivative of the temperature with respect to the volume is equal to the derivative of the pressure with respect to the entropy with a minus sign. You have to think about the minus sign, but all the rest is just conjugated variables. This is conjugated to this, and this is conjugated to that. Right? Life is easy. It's not too complicated. All right. And similarly, well, if you go through it, you will be able to show that dT dN is, so dT dN is equal to what? Let's see who guesses. Without doing the calculation, what should be on the other side?
D mu ds.
D mu ds, perfect. D mu ds. And then minus P dN is equal to what? D mu
D mu d.
dV. That's it. You see, everything is easy. So, and by the way, if you want to remember things a bit better, all the Maxwell relations in the denominator have always the variables that you keep fixed. You see here we're dealing with energy. So the free variables are entropy, volume, and number of particles. The non-free variables are pressure, temperature, and chemical potential. You see that pressure, temperature, and chemical potential are sitting above, and the others are sitting below, right? Now you can have fun yourself and derive all the other Maxwell relations. The only thing you have to think about is a minus sign, is whether there is a plus or a minus. You know?
Which one you fix the denominator?
In the denominator are the variables, the free variables. Entropy, number of particles and volume. In the numerator are the pressure, the temperature, and the, right? So you understand that the ones I will, for example, derive from the Gibbs free energy, in which temperature, volume, and number of particles are fixed, will have temperature, volume, number of particles in the denominator, and the other variables in the numerator, right? And the only thing you have to think about carefully is the minus signs, because all the rest is automatic. You just take them in cross, and that's it. You have to think a bit about the minus signs. But this is not, don't get obsessed by, when you think about this Maxwell. I know that, I mean, I remember when I studied them that it was a mess. And you have to make sense of the mechanism. And then once you understand the mechanism, like in thermodynamics, life becomes easy. But the mechanism is very simple. You have many different situations in which you choose different variables to describe your system. Then you fix those variables, you take those variables as free variables, and we express everything else in terms of, you introduce these potentials, and then you find all these Maxwell relations. That's it. Life is easy. Okay? Now, life is easy now that I'm talking about it, but as we will see next time, when you do exercises, you have to practice a bit, right? Because it's not that straightforward to understand what you use, how to change variables, etc., etc., etc. It's easy, but it's not that easy. Okay, yes.
Yes, in the case of the canonical assemble, the thermodynamic quantity to describe the system is the free energy.
Is the Gibbs, the Helmholtz free energy.
I am wondering what is it in the case of the microcanonical assemble?
Is the energy, the internal energy. That's it. Internal energy. All right, guys. So that's it for today. Next time we will do a couple of exercises, and then let me see. Well, we will do a couple of exercises, introduce the conditions for thermal equilibrium in terms of derivatives of entropy with respect to energy, and then that's it. We will soon start with statistical mechanics. Okay? Great. Okay.